Hello and welcome back to the Hyperthesis. We are at episode 97, and today we're joined by our very special guest, Jon Clarke. My name is Feely.
I'm Patrick.
I'm Liam.
Hi, I'm John.
Well, as you can hear, we have Jon Clarke here today, and Jon, a little bit of introduction. So Jon studied physics as an undergraduate, and he was a senior research scientist at the United Kingdom's National Standards Laboratory. And then he retrained and taught high school physics for many years, going on to run training for a total of 300 high school physics teachers for the UK's Professional Association of Physicists. So he's now taking a PhD in physics at Queen University, doing analyzing data for the Euclid Dark Matter experiment, which I think we had maybe a couple people who talk about the dark matter experiment before. So welcome, Jon.
Thank you. Good to be here.
So today we're gonna talk a little bit on the intro, which is a little astronomy based, maybe a little related to dark matter. So a while back, there is this probe that we sent out, little spacecraft per se, in 2023 called Euclid. And Euclid is on the 6-year mission to explore the dark universe. And during this testing phase in September of 2023, Euclid sent some images back to us so we can see, and they were out of focus intentionally. There's one fuzzy image that a scientist, Bruno Altieri, decided to take a closer look, and he found out that, well, it looks like there is some kind of gravitational lensing that he can see. So this gravitational lensing is called the Einstein ring. So it happens when you have a really a lot of matter, really massive part in the sky where it's enough to bend the light around it. So it acts like a lens where normally if you have something that's obscure, your galaxies that's from behind, you can't see it, right? Something in front. But the light that's angled, come out on an angle from that galaxy, it's getting bent back into the sensors or into our eyes, basically. So we can see the galaxies that's behind because we have this gravitational lens, that this kind of big mass that acts like a gravitational lens in front of it. So apparently it's a very rare phenomenon. And they found that it's not hiding that far away. It's actually the galaxy called NGC 6505 is only about 590 million light years away from Earth. Really close, right? So it's the first time that the ring of light surrounding its center is actually found, thanks to this Euclid that have really high resolution instrument. So it's made of this background galaxy is 4.4 billion light years away, but the light, which is usually blocked by what the galaxy in front of it, is now observed because the distortion of gravity. And the faraway galaxy actually has not been observed before, and so it really doesn't have a name yet. So this kind of tells us that maybe in the following years, we're going to have really amazing results from the Euclid probe that we sent out there because, well, this is just an early, right, during its 6-year phase. So I'm excited to hear and see what's going to come out from this spacecraft and what astronomers are going to find. Perhaps we will find some kind of more, some insights on how dark matter work from maybe we can get a better resolution on this gravitational lensing effect.
So there's a galaxy, and then there's another galaxy in between it and us, and then there's dark matter. Is that what I'm getting out of this?
Yeah, it seems like there's like a massive black hole in the center of galaxy, right? Like
Yeah.
of every galaxy, a supermassive black hole, and there are a bunch of, I guess, dark matter around it. So it have a lot of mass, so it create this strong gravitational lensing. So the galaxy acts as a lens, basically.
So this Euclid mission is really interesting just because it looks at one of the two ways in which we can kind of detect and observe the dark matter. So this is an indirect observation, which tends to happen with these space telescopes. But I know we'll probably be talking a bit more today about direct detection, and we've talked about this before, but this is kind of the original way in which we've actually measured dark matter and the effects of dark matter, more so because we aren't observing it directly, but we're looking for the effects which were first noticed and first proposed by, I believe, Lord Kelvin 150 years ago, where he proposed that there were these dark objects in the sky. And we've talked about this before. So it's just kind of fun to see that these same principles that were discussed 150 years ago, before we even knew what a proton or a neutron or any of this was, we're still kind of using the same approach, but of course much more advanced and refined. And it's amazing the amount that Euclid is expected to observe, because it's going to map something like, I forget the number, but it's mapping a very, very large portion of the night sky, and it's expected to find around 100,000 strong lensing events. So really quite cool stuff going on here.
I thought, okay, I don't know anything about Kelvin and dark matter, but I thought the whole idea was that back when they were looking at, the Milky Way and spiral galaxies and stuff, they have these like rotation curves. I forget the exact details, so someone please fill in for me, but they have, yeah, exactly. You guys can comment on it more, but basically there's this plot you can make, and what you would expect is not what you see experimentally. And they filled it in. They said, all right, there's missing mass from the galaxy, and that would be dark matter. Maybe I'm wrong.
Yeah, so it's indeed the rotation curves are one of the critical pieces of evidence that dark matter is very likely to exist. So as you move further and further away from the center of a galaxy, you would expect that the stars will orbit the center of the galaxy slower and slower. And that's not what we discover. We find that actually they rotate at about the same speed, no matter how far from the middle you are. And at the moment, our best explanation for that is clumps of dark matter. So lensing, this strong gravitational lensing, gives us an independent way to assess how much mass there is in these other galaxies.
Yeah, so it's like you see lensing happening, but it's not like you don't see any mass, but mass has to be there.
That's right.
So dark matter. So can lensing tell you anything about dark matter besides that it's there and what its mass is? Because I think one of the things you want to, I don't know, but if you're trying to detect dark matter, if you know its mass and where it's at, that's one thing. But I feel like you're still missing a lot of information about it. So is there any like other signatures you can find from that, or is that what people are working on with all these other experiments?
I think that's probably a useful way to think of it. That the astronomical side of dark matter isn't my field, right? So it might be that I've misunderstood myself, but part of it is it might give us a way to map within a galaxy where the mass lies. So the distribution of mass across a galaxy, we might be able to do that for the best results we get. What I work on is called direct detection. What we were just discussing is indirect detection. We're inferring that dark matter must be out there, but it tells us nothing about what dark matter's made of. Whereas our direct detection experiment, where we run a detector down in Snow Lab, down this nickel mine, that is, if we succeeded in finding events in there, that would tell us something about what a dark matter particle is. Right. So it's giving us different information.
And the really useful thing about these indirect detections is it gives us an idea of the distribution, because we know that matter itself in the universe is unevenly distributed, so it's clumped in galaxies and whatnot. So with dark matter, again, we can't observe it through visual means, through electromagnetic properties of the dark matter itself, so we see its effects. And there's a really cool visualization, which unfortunately we're on a podcast, so I can't really show it, but showing essentially filaments throughout the universe. And these filaments show the uneven distribution of mass. And so it's very interesting to see and make observations related to, okay, does dark matter kind of follow these filaments? Is this kind of theory correct for different distributions where galaxies are actually connected through these thin lines of mass? But yeah, it will be very interesting to see where dark matter is and also where it isn't, because there are some, I think there is one notable galaxy, the name escapes me, where it actually has a stunningly low amount of dark matter. And so it's actually showing those expected rotation curves if you don't have dark matter. So there's a lot of cool observations to be made for where it is and where it isn't.
I know one thing that these people do is they look at the cosmic microwave background, which is uneven. There's different areas of higher and lower temperature, I guess. And they try and infer from that distribution how inflation might have happened or things that could have happened during that. So I guess, yeah, once you have the distribution of dark matter, you can maybe try and figure out, reverse engineer it and see where it all came from and how that might have started.
Well, I think what we need now, what we want is a high resolution of anything, right? Like maybe Euclid will give us that answer or some kind of data so we can figure out the answers. But so to move on a bit, I think we kind of have a little preamble to dark matter. Well, we had a guy on here before, Jean-Marie, who also works on News G. But just to make me a little refresh. So, John, what do you do in the News G group?
So my own work is data analysis, and indeed Jean-Marie, who was on a while ago, so we're both in the same area in News G. He's a year further along in his PhD than I am. Shall I say something about the detector itself?
If you want, I mean, what do you work with the detector?
Yeah, so the News G collaboration, the main part of its work is creating a kind of detector called a spherical proportional counter. So in SNOLAB, we have a hollow sphere of copper, which is 1.4 meters across. And we filled that with, at the moment, it's got helium and a little bit of methane in it. And what happens, we have a strong positive electrode in the middle of the sphere. So when particles go through the helium, if they collide with the helium atom with enough energy, it ionizes the helium atom. The electron from that, or more than one electron from the collision, ends up drifting towards the electrode in the middle. And that creates, when it gets near the middle, the electric field gets strong enough that the electrons accelerate really hard and they end up ionizing more atoms. So you end up with this avalanche of ionizations, and that's what our detector picks up. So we're looking for particles hitting gas atoms in our detector with enough energy to ionize them, and that tells us something happened in the detector. And obviously what we hope is that dark matter comes wobbling through the detector and does these collisions, and we can look at these events, establish that some events are being caused by something we don't understand, and that it matches our models for how dark matter would behave. So far, we haven't spotted any.
So I think a very common problem with detectors is figuring out what actually ionized.
Yes.
The right. So because they used to have neutrino detectors. I don't know if they still do or not. I think they probably still do, but down there, I don't know.
Yes.
But
yeah.
So with the neutrino detector, right? It's they had all this heavy water, and I don't know if they used ionized. I've been told all this information before, but it all I forget it
Well,
all over
there's
time. But
well, there's a couple of different designs of neutrino detector down there, and the one that Snow Lab was named for, which is now in its form Snow Plus, in fact, they're mostly looking at other bits of physics now. But for instance, there is a separate dedicated neutrino detector in Snow Lab built from spare parts from all the other detectors. And what that's doing is looking for supernovae, because we now have entered this new phase of multi-messenger astrophysics where we don't only have to look at the electromagnetic radiation that's released now of light, infrared, UV, and gamma, and so on, but we can also look for gravitational waves. Not that that's something that happens in Snow Lab, but that's the LIGO gravitational wave detectors, and now our neutrino detectors are sensitive enough that we can do neutrino astronomy.
yes, so I guess, sorry, my original
Oh yes, how
question,
we know what caused it.
yeah, because I know that in these particle detectors, right, you're looking for at least this specific style. You're looking for something that ionizes the helium.
Yeah.
So how do you know that it's like, if you're looking for dark matter, there's probably other things that ionize it, and how do you separate the two? I know that's a big problem, right?
So within the detector, we can look at the shape of the pulse that's created when the ionization occurs, and that gives us lots of information. So, for instance, one of the problems in our detector is that it's contaminated on the inside with some radioactive isotope nuclides. And we think that's come from a bit of radon leaking in. Radon's radioactive. It decays into solid daughter products, which are radioactive. So we think that's happened inside the detector. So we want to rule out things like alpha particles. And so what you end up doing is comparing how many events you get of different types to what you expect from what you know about your background. Right, so we know that there's going to be a certain level of background events. For instance, some neutrinos will come through our detector, and so we can model that behavior and check that everything's happening as we expect. And then as we make our detector more and more sensitive, as we improve its design, we can look for lower and lower energy events. And at some point, if we start uncovering events that don't match our expectations, if we find enough of them, then we could go, hey, look, we may have found dark matter. Actually, what's happened so far is the number of events we find, essentially it matches what we expect. And therefore, that's why we're saying we haven't found dark matter yet in our detector.
So where do you come in? What did you do in this experiment?
So at the moment, what I'm doing is we try different gases in the detector. We filled it with helium for the first time ever back in November. And so my job at the moment is looking at the shapes of the pulses we get when we're using helium, which are different to those we got when we were using argon or neon. And so I'm now trying to figure out, for instance, what shapes of pulses alpha particles create, so we can cut out a chunk of our background. Jean-Marie had done a similar role for the neon, and particularly for the neon that we gathered data in for a couple of years. He's now working at the top level of taking in all the data of different kinds that everyone else is feeding him, including me, and figuring out at the top level, how do we think we've seen dark matter or not. At the moment, if dark matter has certain characteristics, we have the best detector of the world at not finding. So that makes us fairly confident dark matter doesn't exist with certain characteristics, and we're the best at saying it's not there.
Just for those of you interested, you can go listen all the way back to episode 6, where we talk about radon removal from the News-G detector. So that's what I focused on in my master's, was the radon removal from the gas. So you can hear all about the effects of alpha particles, and also Jean-Marie's guest episode, which I believe, well, I'll find it and put it in the notes.
But there's radon in the detector, so your masters didn't get it all.
Well, one of the problems that we hadn't expected, was it turns out that one of the components, one of the things we've put in to improve the gas quality actually it turns out that inside there's a component that we think is leaking out radon. And it wasn't obvious that that was going to be an issue before our colleagues put that component in the detector. So yeah, I mean, this is the fun of doing something new, right? This is all groundbreaking research, things we're doing nobody has ever done before. There are similar-ish detectors around the world, so we're not alone. But no one, I think, could probably have warned us that thing had radon in it. So we learn as we go. Now we've put a radon trap in to capture the radon that component's leaking out. So
They're such sensitive measurements, right? That it's like impossible to predict every single thing that will affect it.
Yeah.
I guess I'm wondering, how do you know what a dark matter signal looks like? Because I know there's all of these different theories and models of what is a dark matter particle.
Quite. So if dark matter exists, right, we know, and that's not a given, right? It looks incredibly likely. All these indirect detection techniques, everything from cosmology and astronomy, makes us believe very firmly that it exists, and dark matter is the best explanation. But we still haven't seen it directly in our experiments or anything like ours. Anyway, but if it exists, we know the kinds of properties it must have. And you mentioned, indeed, there are a multitude of models of what dark matter might be. So our experiment is focusing on a certain set of those models. For instance, a broad range of models were predicting the existence of dark matter particles with a certain mass range. And in fact, that mass range has now been very well explored, and no one found it. Whereas we're looking at stuff which is a subtly different set of models, where actually it will be lighter than those other ones predict. So we know that it shouldn't be charged. For instance, that means it will behave somewhat like neutrons. So one of the tricks we can use is to put a neutron calibration source in our detector or near the detector and see how the detector responds to these neutrons of known energy. So that's something we do often. Because if dark matter particles exist, they must be electrically neutral, so they must have some characteristics that make them behave a bit like neutrons or neutrinos or whatever. So yeah, it's tweaks to thinking like that.
Well, I was hoping to keep the physics part brief, but since we bring up physics in this room, we're gonna talk about it for a bit. But to move on into more the education side, would you tell us what you did in the UK? And from the introduction, you train teachers and such. What exactly did you do? And
Okay.
well,
I wasn't sure how long to make the list. Okay, so I had worked as a research scientist. For various reasons, I found that particular role a bit frustrating and ended up deciding it because I'd always been interested in teaching. One of the last things I did as a research scientist was help run a week-long training course for other people working in our field. And I really enjoyed that work. So I retrained to teach post-compulsory, so teaching kind of college and university level. And so that's a year full-time in the UK. I worked in what England would call a sixth form college. So it was in Quebec, it would be called a cégep. So I was teaching only grade 12 and 13 physics. I did that for 8 years, ended up as the manager of that department. Of the physics, 17 physics and chemistry lecturers, did that for a couple of years. Worked for the Institute of Physics in the UK. Most high school physics in England is taught by people who haven't studied physics since they were 16. So it's mostly biology graduates, and they chose not to learn physics after 16 because they didn't like it. So really my job was to make the biology teachers less terrified of physics so that the students had half a chance. Go on, Liam.
Oh, there's a very similar thing in Canada where a lot of high school physics teachers, maybe in university, they took like a physics course once or a calculus course, right? So like my high school physics teacher was a chemist, so he took a bit more physics than most of my friends' high school physics teachers took.
Yes, yeah. I mean, it's an issue beyond England. England has a particularly acute problem for various reasons, and part of which explains why I'm preferred to be unemployed in Canada for a while than continue teaching in the UK. But anyway, I'm here now. So I would do things like I would go into a school with their existing science teachers and run, for instance, a session about Earth in space, and just get them to think about gravity and satellites in a way they might not have thought about, and that challenges the teacher's own understanding. So that we can draw out any misconceptions they hold, which means that then they could be more effective with their students. As part of the project, I also ran kind of shows if they wanted me to put on a show to all the students, just kind of do fun, whiz-bang, physicsy stuff. I'm particularly trying to make sure I trained one of their teachers to be able to carry on the show and encourage them to teach a very different style of physics lesson than they might have done before. So it's more about exploring a phenomenon together that nobody in the room would have looked at before. And it was emphasizing the fact that real physicists don't just sit there endlessly applying known equations. If that was the job, then we wouldn't need physicists. It's more about doing physics authentically. And so, stuff like that. I really enjoyed it. Go on, Feely.
Well, so it's from what it sounds like, it sounds pretty free form. It's like, you go do this stuff, but
Yeah,
in school, usually they have curriculum. Then there's,
yeah,
let's say, grade 11, they have this
yeah,
specific material, or let's say,
yeah,
I don't know how it works there. Like maybe physics 1, physics 2.
yes.
When you go in, are you expecting to do like on specific topics that, let's say, it's going to be on exams, or is that an emphasis at all?
Well, I had a great amount of freedom. Okay, it was really interesting to do that job for 8 years because our managers had a similar background, and they recruited people who they felt were better at this than they were. So we had this incredible team, and we have about 50 of us across the whole of England working together, trying different approaches. When I negotiated my support for an individual school, so I worked with one department ideally for 2 years, I would say to them that I was best used if I was looking at the kind of the strategic, broadest, most fundamental stuff. They could indeed ask me to do something quite narrow, like, our students have this exam coming up. How can we help them best? But I pointed out that was kind of a misuse of me as a resource, because one limitation is the teacher's own understanding of physics at the level they need to explain it to the students. So a devastating exercise that we ran in almost all our schools, because we know, for instance, that no matter what the details of the curriculum, everyone needs to understand stuff like forces, a bit of astronomy, a bit of electricity. So I tended to offer sessions, at least 2 sessions in each of those things. And I would do, for instance, in the forces session, I'd get the teachers to sketch the force, the free body diagram for a tennis ball when it's going over the net in a tennis match. It's England. We do it when Wimbledon's on, the sort of thing, the Wimbledon tennis tournament, right? And almost every single time, the teachers would. Very rarely did any teacher get the answer right. And so their temptation as non-physicists is to make sure that the ball has 4 balanced forces on it. Right, and so they just keep adding arrows until there's 1 in each of the 4, directions: up, down, front, back, and so getting them to trust me so they could reveal to me their misunderstandings allowed us to then really get at why that's the wrong answer, which then they could get right with their students. So I tended to be tackling things at a very fundamental level, which was probably much more powerful than narrowly helping them scrabble for whatever their next deadline is. And that tended to be very successful. One of the outputs from this was before and after we would get the teachers to anonymously say how confident they felt teaching a topic. And what we found was a very statistically significant improvement in teachers' confidence, because finally someone was there trying to explain this stuff, all the stuff they probably feel too nervous to discuss with their colleagues or their boss. I was there, I wasn't in their management chain, I'm not a government inspector. I'd get them to trust me, and then we could really work to help.
Yeah, I guess that's kind of cool that it's like they're used to teaching these very specific problems, that it's like, yeah, the tennis ball one, it's kind of a funny example because they're so used to like, here's a block on a slope or something.
Yes,
and there's always like,
Yeah.
a bunch of, there's always like some normal force and all these other things that all kind of, so it's nice that that's something. I wonder if they have, I don't know if they have anyone in Canada who has that kind of similar job to you.
Well, I'd explored some of this because when I moved over here, I'm trying to decide how unpatriotic to be to the UK. England's education system has some notable successes. For instance, if you look, there are these international comparisons of student learning every 3 years. England's students do well compared to many other European countries. But England is beaten by Scotland, which runs its own education system, and Scotland's is always best. And the features I do not appreciate about England's education system are all completely missing. So it shows Scotland's success shows that those features are utterly unhelpful, and we should just ditch them. But where was I going with this? Go on, Liam. What was your last thing you said?
Is there anything like any roles like the one you had in Canada or
right,
like
that was the point, right? Yeah. So for instance, Ontario, in Canada, each province and territory runs its own education system. Ontario's education system is actually world class. It is nearer to the best in the world in these comparisons, places like Finland, than it is to say Germany, which is not especially successful. So Canada has done a better job in its most populous provinces. So when you look at the results from Quebec, Ontario, BC, they stand up incredibly well. So there's less need for that role. So selfishly, I was disappointed to find that Ontario's education system is in less chaos than England's, and therefore my particular niche skills weren't needed at all. It's great for Ontario. It was great for my one child who moved over here age 13 and has done high school in the Ontario system. It's good for them, but selfishly it meant my career took a hit. Feely.
Well, I think the important question when you put those, kind of statistical facts out, this doing better. So what is the method of assessment? And sometimes you have these kind of like exam where people sit down and answer questions, right? Maybe multiple choice. Is that really the way to go when you go about assessing students? So you just say you compare Ontario to the UK or even in Canada itself. Is it really about grades, or are they really should there be some kind of standardized exam? What is the proper method of assessment to look at students and say, hey, they're doing well or they're not?
So, you've hit on something important, which is any assessment method is imperfect. And actually, I'm going to digress a moment because, Feely, you'd asked me what I'd done. To mention something else I've done, for instance, I peer-reviewed for a physics education journal. So I've done 115 peer reviews, I think, for that. So that journal covered from start of high school up to introductory undergraduate. And so I've got a background in evidence-based teaching, and I increasingly used it in my own teaching and in the training I ran for other teachers. No assessment's perfect. What I tend to trust is the fact that quite different assessment methods tend to give different conclusions. Right. So when I say that it looks like Scotland's system is more successful than England's, for instance, for teaching science, there's more than one evidence stream that leads us to that. And so, for instance, the particular assessment method project I have in mind, where of course my brain's just gone blank, this thing that's done every 3 years by the OECD, the Club of Rich Nations. They have a standardized test that is given to a certain percentage of high school students at a certain age in every country that wants to participate. And that's one assessment method, right? But you also look at things like the peer-reviewed literature has come up with a very well-tested set of things called the force inventory. So if you are a high school teacher or indeed a university professor, you could just go use this peer-reviewed force inventory, which asks a whole series of multiple choice questions that really tease out whether the student has understood the fundamental concepts or not. That stuff's gone through peer review so many times, been used so many different ways, and you get a similar message from things like that you do from, say, just looking at England's high school grades. So these different strands which attack the issue in quite fundamentally different ways do tend to give similar conclusions, which as a physicist, over my career, I've gently been teased out of only being a physicist, first to being an educator, and then I now also see myself as a social scientist. It's that sort of stuff that helps me trust the social science conclusion. Sorry, Liam, you had a hand up.
Yeah, it's just like, I guess you kind of need these standardized things that like everybody does the same thing in order to meaningfully compare. Because it's like,
yeah.
At least I'm from Eastern Canada, so where I'm from, it really kind of depends on what school you went to and your teacher on what your grade is, right? So you apply university, you can get people with the same grade, but they have vastly different knowledge on a subject.
Yeah. So one of the big picture conclusions that we're led to by one of the big international figures in the world of evidence-based teaching. Whose name again? I should have written some names down. But anyway, he's a New Zealand professor now working at an Australian university. His name will come back to me in a minute. He argues that overall, the biggest effect you find in affluent countries is actually the socioeconomic status of the household they came from. Then within the control of the school, so schools do have an impact, although it's less overall than that. Within the school, sure enough, which teacher someone has is the single largest effect. And we know, again, the peer-reviewed literature is full of all this stuff about effectiveness of teachers, because obviously in all education systems worldwide, the single biggest budget item is the salary of the teachers. And that's true everywhere. Teachers, they're professionals, they're paid. And so you want to make the best use of that resource. And we've known for at least 3 decades what kinds of things effective teachers do that we could train less effective teachers to do. Which brings me to my particular interest now. I'm in a new setting where I'm at university, where it's very interesting seeing the work specifically about universities and the ways in which universities generally worldwide are decades behind where schools are in terms of engaging with the peer-reviewed literature. So,
Well, that was interesting to hear. And the fact that the biggest factor is the teacher. I mean, my high school physics teacher actually has the undergrad physics degree. Because in my country, you went to teachers college. Actually, I think as an undergrad, that it's like a full 4 or 5 year program instead of like a short one like here.
And sometimes, as it were, an outsider, someone who actually teaches physics as a non-specialist, they can be incredibly valuable. All right, so when I was head of department there, I was involved in a particular hiring decision where we ended up hiring someone to teach some of our physics courses whose first degree was in Italian. And so she brought all the enthusiasm of a good teacher and also brought the fact that she had not been trained to think like a physicist. So she was much more able to engage with why her students were struggling, because she struggled in the same way. And so some of the less effective teachers who happen to be physics specialists, some of that limitation is they can't see why the students are struggling. I'd say the entire first year I spent in the classroom was me learning I really, really needed to bring it down to the right level. I just kept assuming too much of the learners in my room because I've been thoroughly accultured and brainwashed to think like a physicist.
Well, but in a classroom, let's say proficiencies of students are different. Like I love that the fact that I had a teacher who knew physics well because I want to go faster, better, and do more and more and more. But I can see some of my peers were struggling, right? And I can understand sometimes you have people, let's say, don't do physics and explain it really well to people who
Yeah.
maybe not so interested in physics. But at the time as a student, I didn't care. Why would I care? I want to learn more physics. So why would you leave me slower? It is strange. Like what was the evidence say?
Well, we don't have to do that, right? So one of the strengths of a good teacher in this kind of way, like I don't know all physics, right? There's this idea that a physics teacher in a high school might perhaps be supposed to know everything, and a certain style of teacher might reinforce that message, which I think is deeply unhelpful. But one of the things I always used to make sure I did with any group of learners was explicitly bring a piece of physics into the classroom I didn't understand myself and explore it like a research physicist would. I don't know what the outcome will be from this experiment because I've never done it. And I've never seen it done before. So we're actually going to be authentic physicists. And an approach like that can help even the most able, most competent learner in a room become a better physicist themselves. It doesn't have to be about me telling someone another piece of physics. It can be about helping them explore the physics themselves. And there's many ways to do that. And indeed, there's actually a lot of evidence that teachers who push their students beyond their syllabus, their students do much better in any standardized exam. So
I think it comes to a very fundamental question. I want you to maybe a little define a bit.
yeah.
For what would be, if you can like succinctly explain or put into words, like what would be the goal? What is the goal of teaching? Like how you look at what is teaching? For example, like, some people say, oh, like a lot, like, oh, it's to get the whole group of people, educated or what, or some people is more individualized where it's like, no, it's about helping a student, each individual person be better version of themselves and such. Like, what is your view of what is teaching and learning?
Okay. So at a very fundamental level, I would phrase it in terms of teaching a student so they can do something afterwards they couldn't do before. It might be explaining a piece of physics. It might be doing a certain calculation, right? But so a classic piece of conventional teaching, I think, in all vaguely affluent countries, is the idea of planning a lesson where you set what the learning outcomes are. What are the objectives that you want? And you always try and phrase them in terms of active verbs. Afterwards, a student will be able to say, I don't know, explain the motion of a ball with, using Newton's laws of motion, right? And so then there's a concrete outcome. And you can then grade, you can have differentiated outcomes. You can make something that is more straightforward for a student who hasn't grasped it so well yet. You might have some that pushes the most able students. At a different level, I also, especially when I was teaching junior high school, as part of the compulsory English school system, there I also have different objectives. My aim is by the time they finish their compulsory learning of physics, that they've all felt successful enough in physics and that it was interesting enough that they could see themselves choosing to continue in physics. Even I don't think everyone has to become a physicist, but what I wanted everyone to do was have a sufficiently positive experience they could imagine it as an option and they could see why they might want to do it. So that was giving them basically career options and choices in their educational life. Then there's also the thing of trying to let them leave school as informed citizens. Physics comes up all the time in crucial things. Like at the moment, climate change is obviously a massive thing. Giving my students the tools to evaluate scientific questions in the political sphere that might, for instance, help them decide who to vote for, that sort of thing, then I feel I've done my job, right? If they can leave school feeling they can understand a debate like whether Canada or the UK should open more nuclear reactors, things like that, then I feel I've done my job in a very fundamental way about what school is for.
So to expand on that, a lot of times when we talk about physics, there's this stigma around that, oh, it's so difficult. And I think among students, there's this idea that physics is really hard to approach. And I think, we all have peers, or even right now, I'm doing PhD and I feel like, why is physics so hard, right? So,
hold on. First of all, I see that as a failure of the school systems overall. The fact that it has that stigma, and actually, selfishly, as a manager, it helped me significantly. I was the head of 17 physics and chemistry lecturers in this sixth form college. The head of biology, who oversaw a similar number of biology lecturers, every year my results looked good compared to hers. And it was largely driven by the fact that in the England system, which forces students to over-specialize, they would only do 4 subjects. If they were vaguely academically minded, they'd only do 4 subjects at our level. No student would pick physics as a 4th option unless they wanted to do a physics career, right? They'd either come in and do like math, physics, chemistry, whatever, or they wouldn't do physics. But lots of students came in going, oh, I enjoy biology. They picked biology as the 4th subject. And it actually turns out at that level in England, physics and biology are almost identically hard. But because they perceived biology as easier, it led them to make a slightly poor choice, which ended up making my department's results look better. Sorry, and actually, Feely, you were going to ask a question, and I interrupted.
We have this stigma on physics being difficult, and you kind of put it as like, well, maybe it's just a perception that the physics is difficult rather than the actual difficulty itself. But sometimes when you look at the materials, physics used a very specific set of skills, basically. Especially a lot of people are intimidated by mathematics.
Yeah.
To be able, mathematics itself are discouraging for a lot of people, and physics kind of are built on mathematics. You have to be able to understand mathematics. So in a sense, I understand why people are kind of discouraged from doing physics. But is there a way, or in your experience, like to break down that barrier? It's like, is it enough to say, oh no, it's just easy, but like it's
it's so. For instance, one of the things again that worked in my favor, these biologists who came into our college and started studying this particular thing at grade 12, the very first unit they hit in biology had far more maths in it than anything we hit them with in the first year in grade 12 physics. They had to deal with the stats unit, and they found that horrifying. So one of the issues, particularly in the schools I was supporting, is things that the physics curriculum within it, the school, wasn't well designed. So you'd find things like the physics teacher, when they were teaching grade 9, would have to teach their students a whole bunch of math so that they could then teach them the physics, and they'd be doing all of that 2 years before the math department taught any of it. And so there's this thing where if schools and school systems overall chose to make learning physics a priority, there's a whole bunch of things they could do systematically that would make that work much more smoothly and leave their students able to learn physics without making the content any easier. It's about what order we choose to teach things. It's how we choose to teach it. It's things like that. And then we could leave our students feeling that physics was only as hard as biology, which objectively appears to be what a bunch of evidence points to.
Well, I remember even in our undergraduate at university, that was the case too, where we didn't learn the math before we learned the physics. And so a lot of the times it would say, oh yeah, here's a closed integral. Don't worry about it. And then 4 years later, we actually learn about it. So that almost seems a problem with physics education in general.
There are many good things about the department where I'm at now, right? There's a bunch of stuff here that's just best practice. But there's also stuff that isn't. And if we could move the stuff that isn't halfway towards the best practice, it would help immensely. But so one of the examples is in our engineering physics courses, I think they do a math unit that is taught, math course that's taught in the math department, right? And so they do a bunch of differential and integral calculus, but they never ever see it in a physics context while it's being taught. Then they get hit by a particular unit in the physics department where suddenly this stuff that they have used and practiced a lot is used in a completely unfamiliar context, and the new context isn't taught explicitly. And so having worked with high school level students for so long, and also having another thing I haven't mentioned yet is I've also tutored university level students. I know that in itself is a barrier. So I know that would be worth at least a whole class just to say, this is what you did in math, where you did it all in X, Y, Z. Now we're going to do it in physics, and it's going to be F and A and all this stuff that you just haven't thought about in that context before. And that is genuinely enough to throw people, especially someone who isn't feeling that confident in physics. So, yeah.
Yeah, this is something I always complain about, or I don't know, I bring it up a lot about how like language is just such a big deal. And like,
yeah,
from my point of view right now, since I'm in my PhD, it's all about research. Like, I read a paper and I'll read it for 2 hours and then realize that they're talking about the exact same thing I'm talking about, but we just approach it from two different points of view that it's you don't even realize.
One of the evidence-based teaching conferences I went to had a very interesting session on what it would look like if we taught physics as a foreign language, right? So if you think about how many new words, how much new vocabulary a foreign language teacher will present, particularly if we think, say, grade 9, grade 10 lesson, right? How many new words will that, say, French or German teacher present in one lesson, right? And without thinking about it, the physics teachers present stuff all the time. If you'll forgive me one moment, we've got a guest in today, and I'm going to invite her to use my desk because I've stolen a little cubicle off to one side. Give me 1 minute if she's still there. Oh, no. She's solving herself a different way. Right, sorry about that. Yeah, I stole a little cubicle off to the side of an office. If I may, I wanted to focus on physics teaching at universities as part of what I say today, because it's a big issue. So in the peer-reviewed literature, one of the things it focuses on is these achievement gaps, which should arguably be called teaching gaps, between students from different demographic groups. Right? So there's a lot of evidence that students who are from groups that are underrepresented in physics, right? So, for instance, women, other gender minorities, in a Canadian context, if you're Indigenous, then there's a lot of evidence that poorer teaching disproportionately harms those learners. It means they learn less than the other people in the class, whose own learning is already being harmed by the poor teaching. But people from these underrepresented groups, their learning is harmed even more, and they're more likely to drop out of a course or fail it or whatever else. And so that's part of why physics is still predominantly white and male and all the rest of it, and their socioeconomic status. And so one of my interests is seeing whether I can help, given my unusual background as a physics PhD student, whether I can help the course instructors in this department engage more fully with what the evidence recommends. And in ways, that's a tough sell, because I think there's an element, I would go so far as to label it as physics chauvinism. There's a thing where physicists are all too happy to believe that physics sits at the top of the science tree, and that anything that's not physics is inferior. And I mean, physics has been enormously successful. We've made huge progress in fundamental questions in a way that, say, psychology hasn't. Now, I'd argue that's not because physics is better or physicists are smarter. It's because social science, like psychology, are tackling more complicated phenomena. They're just as smart as we are. They've, in their own ways, made just as much progress, but it's a messier subject. And so one of the barriers particularly faced by trying to get physics professors to engage with social science evidence is it does come from social science. It requires persuading them to give peer-reviewed evidence from these very different fields that they might even look down on, to give that a fair chance. And that is actually a tough sell, especially where traditionally universities have not trained their instructors. High school teachers will typically go through a year full time, if not 2 at university. They go through a year of close supervision and support. They might have a class of theirs observed every year for the rest of their career. By contrast, your average physics professor may well have received 0 hours of training in any of this. And so it's,
John,
yeah, go on.
there's a lot to unpack there.
Yeah.
So I'll go start with you mentioned the social science doing something complicated. Like there was this paper, I think Liam, I think you might have read it. They call More is Different, and I think my supervisor sent it to me. Changed my life. It's all about breaking down this hierarchy of science, where physics is more fundamental. Well, we can talk about that at a later time. So I think the point I want to make is like, I think there's a fundamental assumption that people make when you teach or when you involve in education, and one dangerous one is like, well, when I do this, some students are just stupid and cannot understand this. So it's not really, let's say, my fault. Because let's say there's 100 students and 40 of them don't understand physics. Oh, well, maybe that's just a physics problem. It's not a teaching problem. And it seems like maybe that's happened more, at least when I was growing up in Asia, where a lot of things about testing, and there's so much assessment where, well, maybe you're just terrible at it. Well, perhaps it's the teaching problem, it's not the student problem, because the way you put it, it sounds like, well, everybody have the almost like similar, same capability. That's why maybe the issue is in minority groups or people who have lower socioeconomic status have worse results. Perhaps maybe that's not because of the students, because of the teaching. But
Absolutely.
I can see quite a number of people maybe in the past have thought that, well, perhaps there are certain people just worse.
Yeah, well, to offer 2 ideas there which are related. So in the world of psychology, you have the work of people like Dweck. So there's an idea called a growth mindset. The idea that no matter what we're talking about, we happen to be talking about physics, that you could always teach someone to do something better. Right. And so it's that, at 2 extremes. You could say either people are born to be physicists, they're born to be smart, or whatever you want to. At the other extreme, you got the idea that you could teach someone intelligence. You can teach someone to think a different way. You can teach someone to become a physicist. And so more and more often in high school systems, again, particularly in affluent countries, you'll see teachers being trained to think from that growth mindset rather than having this closed view. Oh, well, that student did badly in their test last year. They're a new student to me. They're just never going to be good at physics, so I won't bother. Where the peer-reviewed evidence suggests that is the wrong approach. So there was a second thought I had, and I've already forgotten what it was. Anyway, yeah.
I kind of believe in both. Like, I think some people are just born and their brains work a certain way and they're better at some things than others. But I still think that like anyone can be anything with enough work and being taught the correct, like the right way. And
yeah, indeed. I mean, it's not as if everyone. It's possible that not everyone could indeed be trained to do the best physics that's being done in a university, but certainly we can teach anyone to be a better physicist, understand physics better, and appreciate physics better. We're all physicists, right? We all love physics enough for whatever reason that we're still doing it. We've been doing it for years, right? At least we can help someone appreciate what we enjoy about it, or find something else that they particularly enjoy about it.
So there's a trajectory I want to go into, but I'm going to take a detour first into teaching style or method. There's this fad called, active learning that was really popular in the literature. Let's say,
I love you hearing describing that as a fad. Okay, we're going to come back to that choice of word. Go on, Feely.
Yeah, because it seems like you gotta teach people here. No, everyone, please use active learning is
right.
being pushed a lot, and And at the time, nobody really actually, at least in my experience, never told me more like an evidence-based teaching. It seems like the active learning was the holy grail of teaching, at least the way I felt like it was being offered to us. Like, no, you gotta use active learning because really this is the thing. And I want you to comment on like, what is active learning, and is that a thing, or is it my characterization of it as a fad just incorrect?
Wait, Liam, did you want to jump in first?
Yeah, because that's just like that's what I was going to ask. I don't even know what active learning is, and it kind of
Oh,
comes
right.
back. It kind of
Yeah.
comes back to the point that like in universities they don't really teach people how to teach. Like even
Yeah.
as a PhD student, I have to TA. Like most people have
Well,
to.
we'll get to the post-secondary. But
Yeah.
Yeah.
So with my background as a trained school teacher, right? So what universities call active learning hurts my soul. As a phrase, it hurts my soul in two different ways. So it describes what school teachers have a special word for. It's called teaching, right? And so the main instructional strategies traditionally used in universities, which are clearly still used by a lot of course instructors in a lot of courses in physics departments worldwide. All the peer-reviewed literature I've ever seen says it's wildly ineffective. Right. So what they're doing is contrasting active learning with passive learning. The idea that in a traditional lecturing format, an instructor stands at the front and basically just provides information. Right. They say it or they present it on slides or whatever it might be. Right. They're just presenting stuff. And the students never do anything in that class other than be a passive recipient of this information. And that is a utterly ineffective way to teach people. It's as ineffective as two other roughly equally rubbish methods, which is reading books and watching videos. And where it fails is because it doesn't follow any evidence-based pedagogical principles whatsoever. So by contrast, what any teacher who really deserves that label would do in a school is perhaps they present a piece of information, but the real learning occurs when the students then use that piece of information to do something. Right. So active learning, as I say, is what schools just call teaching, which is part of why the phrase annoys me. And it's so to contrast a course where, for instance, students could sit passively being read something for 30 hours versus being presented something and then being asked to solve a problem with it or to explain what it means to someone sat next to you. Because being a passive recipient of information doesn't address any of the reasons that I haven't learned it already or I don't understand what's being said. Right. So instructors are often talking up here and they're rushing through whatever they think they need to tell me in 2 hours, whereas actually I've got problems down here. And if they just spent 5 minutes addressing my misunderstanding down here, then I could understand what they're talking about up here. But that passive lecturing model never allows me to do any physics as a student, and therefore my misunderstandings are never exposed or addressed. So this active learning model, which should really be called an active teaching model, because it isn't about learning, it's about teaching, that would at least give some time in any class where the students themselves would do some physics. And that all the evidence says they learn far, far more physics if you do that. And there are various different strategies you can use within that, but that's the core of it. So at the moment, lots of university professors who've been through a mostly traditional method, what that does is train them to believe that it's appropriate, and it isn't. That's the core message. They believe that if they allow their students to do some physics, that's harming the learning of the students because it means the professor, for as many minutes as the students are doing physics, the professor isn't telling them new physics. And so they feel they're letting their class down because they haven't wedged enough physics in them in that class. But it overlooks all the evidence that, like some horrendously high proportion of what they say isn't understood or learned. So it's mostly a waste of time.
I completely feel that, because even in grad school now, like we took all these classes in undergrad, and like we had what I consider to be some pretty good profs, but now that I'm in grad school and I'm having to like teach some of these things, I have to go and like do everything myself. I was like, wow, I did not understand that at all at the time, and I feel like I really get things now. And like even when I read a paper, I can't just read a paper. When I read papers, and if I really want to understand what's going on, I just have to like, open up like a book, and I have to like redo the whole paper. I pretty much have to like rederive everything they did and make the plots to really understand it.
Yeah, I mean, I understand each logical step which has led to the current situation in many physics classrooms in universities. But from a pedagogical point of view, it just makes no sense whatsoever. It's a complete misuse of resources. Like the idea that you have these world experts in their field, and in essence, what they're doing is telling you stuff, where the vast majority of what they tell you nobody in the room can understand, compared to you have this world expert in the room, get the students to do some physics, and then this world expert can go, oh, no, that's why you get the wrong answer. This is the wrong idea you've got. It's so much more powerful. Annoyingly, at the grad level, there's very little published about graduate science courses. It's possible I've read every single paper, peer-reviewed paper, ever published about physics graduate courses. There's only like 15 or 20 of them or something. And none of those have a decent sample size. The quantitative ones don't have decent sample sizes. But what they have published shows it's consistent with where there is a decent sized, it's not quite a mountain, but there's a decent sized hill of evidence about what works in advanced undergraduate courses in quantum mechanics and things. And sure enough, it's exactly the same as you find is effective in high school. Right? And so it hurts my teacher soul to see all this ineffective lecturing, knowing that a tweak to what they do, it doesn't have to reinvent everything they do, but a tweak to what they do would make it so much more effective.
Well, the one of the new words that I learned, well, not learned, I knew the word, but like was not used in, let's say, primary and secondary
Yeah.
school at all is lecture, like
Yes.
lecturing.
Yeah.
That I
Yeah.
never heard that
Yeah.
used until university. It was like, oh no, this is a lecture. You go to a lecture. Where in school, you just go to a class. You go to teach, someone teach, right? Or you go learn. And the fact that lecture, I think the connotation that's come with lecture is like someone's on the front of the room lecturing. They're not engaging with you. And one of the things that
there was an irony to my first job title when I became a teacher, in that because I happened to teach in what England calls the sixth form college, my job title was lecturer. But actually, that was the only thing I didn't do ever in the 8 years I worked there. Everything I did was teaching. Anyway, sorry, I interrupted again.
Well, there's this idea that the difference between, let's say, doing and teaching. It's a lot of time people who do research in the university level, in professors and stuff, they do science, but they're trained very well to do science, and there's very little training, I think, as you mentioned before, on teaching science. And I wonder what would be like the next step. How can we teach people to teach better?
Yeah, because like one of the Gedanken experiments I like to do in terms of education is to imagine if a country decided to run its school system in the same way it runs its exams, right? So you take all your trained teachers, you fire them, right, because they've been trained, and then you just hire people off the street who've done some physics, and you give them no training, and you say, off you go. Because that's really what most universities do to their physics instructors. And so anything is an improvement on that, right? And so, for instance, Queen's University, where I'm based, it's coming up to its 200th anniversary of its founding. The principal of the whole university has published this discussion document to kind of make some strategic decisions. And my heart leapt when I saw that one bit of it is a potential commitment to train every single instructor in the university. Now, brilliant. Now, the moment you give someone 1 hour's training rather than nothing at all, that's an infinite improvement already. The idea that you could actually take it seriously, because these instructors, like, think of a new physics professor, their first ever year as a prof, they will probably have had 4 years as an undergrad, plus another 2 in masters, plus another 4 as a PhD, so we're at 10, plus at least 2 of a postdoc. That's 12 years. So they've had 12 years of dedicated training, making them to be the best evidence-based physicists they can. And they've had 0 hours, let alone years, 0 hours of training to be the best evidence-based teacher they could be. So anything's an improvement.
Yeah, that's always been crazy to me because like even like not even being a professor, but like TA in classes, I showed
Yeah.
up to McMaster, right? And they're like, "All right, you're gonna go run this first year engineering lab."
Yeah.
Never, and we got a bit lucky because during our undergrad, we all TA'd because we went to a small university. So I TA'd as a second year, a third year, and a fourth year with no training, right? You just go and you help her out. But like I had that experience, and some people they never taught anything in their entire life, and they're like leading a lab, and it was crazy to me.
Well, especially when they're doing it in a second or third language as well. So yeah, one of the things I did when I joined this department as a PhD student was because of my background, and I started a teaching and learning discussion group here. There had been one that was led by one of the profs in the department who is particularly keen on evidence-based teaching. He's a fan of what's called the flipped classroom, tends to use this in all his classes and things. So he used to run that. COVID killed it. So I kind of helped bring it back to life. And kind of a part of the spin-off from that was the fact that Ty Withers, a master's student here, they ended up saying, well, let's do something about it, right? So they came up with a half-day workshop for all the new grad students. They brought in Melissa Diamond, who's a postdoc here. Melissa had created a similar workshop at Johns Hopkins, where she did her PhD. And so the three of us cooperated, brought in other experienced TAs, and we ran this, whatever it was, 4-hour training workshop, which the students valued immensely. And we applied all the logic that I would hope to see, where it was about an authentic task. The core of that workshop was we got some of the experienced TAs. Each of them was assigned a personality for that session, and they'd go in and we get the new TAs to teach them something. And it was really fun because you had people coming in saying, right, I'm not going to help them at all. I just want them to tell me the answer. Things like this. And it made it a really authentic task. And like someone came in who's a complete panic. They've got an exam tomorrow. They don't feel they've understood anything. And making the new TA deal with this kind of emotional high stress situation before they had to do it authentically in the classroom. Yeah, the new students really appreciated it. So
I
I'd
was
love
one
to
of
see.
the actors.
Yeah, indeed. I feel it was very effective. And one of my friends and colleagues in this department, Emma Ellingwood, who's just finishing her PhD and about to go off and do a postdoc in Edinburgh in the UK, she did her role so well that she was described as belligerent. That is the last word I've applied to Emma, who is quite shy and deeply lovely. Anyway, yeah. So anyway, anything that was actually authentic and helped the professors really engage with what it might mean to help their students learn, anything like that immediately is going to make a big difference for any professor who's open to that idea they could do their jobs better.
I would have loved to see Feely do that role. That would have been incredible. And I would love to ask you more about teaching during COVID and your thoughts on that, but we're running out of time. So maybe that's a conversation for another day. So I think, I don't know, Feely, we might have time for 2 more questions. But my one question is, like, what got you into physics? So, like, when you did an undergrad in physics, why did you do that? Like, what influenced you?
So a very common story, it was my physics teacher. So often when you speak to people who are into physics, often a particular teacher does show up, especially for something that has a reputation of being hard, right? Society's done a terrible job overall at encouraging people to think of physics they might want to do. Also, nobody in my family before my older brother had ever been to university. So my older brother was the first in our family to get a degree of any sort from university, as far as we know. He got an ordinary degree in engineering. I was the first to get an honours degree. So because this teacher had made me think that physics might be for me, so I ended up, and in fact, I'm rather proud of the fact that I went and did theoretical physics at Oxford University. And so it was like, so to go from no idea what university might be to go being there was quite an interesting experience. And I mean, there was lots I could quibble with, especially about some of the teaching. But nevertheless, I left 3 years later knowing a lot more physics. That's what I went for, And so, yeah, and aged 18 in the UK, when you need to make a choice, I could have gone down physics or chemistry routes. And for me, it was the fact physics was more fundamental. It tackled some bigger questions. And and I've always enjoyed it. So I began my undergrad in 1991. Says something about how old I am. So I've enjoyed physics mostly for whatever that is, 34 years. And I've always done something that related to physics. And I've been lucky enough to be supported by my parents, who themselves weren't familiar with the university. I've been made to feel it was something I could do, and it's given me an interesting and varied career. And that's been an absolute pleasure. I'm really glad to have spent my time doing this stuff.
Well, before we get to the last question, we always ask our guests. I think I'm gonna take a little bit of the crux here that what we've been talking about. That what I noticed, one thing you mentioned is that, well, in the physics in the undergrad level, it's actually not that much more difficult. It's just that the teaching is worse. I think it's a good to note that well, perhaps physics is not that such a feel seemingly difficult degree. Maybe it's because the teaching that's happened in the post-secondary level is just poor. And
to make sure I don't get too smug as a high school teacher, right? Then they've got a different job than we do. And in fact, they have two different jobs than high school teachers do, right? So most of a professor's time and most of what their career progress hangs on is their research, right? So really, they're a professional researcher who is an amateur instructor on the side. So that's one problem. High school teachers, that's their only job. We might do other things to do with the career, to do with the school or whatever, but really, the vast majority of what we do in a week is about being a teacher, and that's not true for them. Also, there's a difference of scale. Our first year engineering physics classes can be 800 students. So, the biggest class I was ever required to teach was 28, I think. So the scale of it is genuinely a different problem. And we can equip them with properly trained TAs and everything else. There are ways to solve it.
Well, there are factors and all these things, right? But at the end of the day, the result is that it's not doing well. So
yeah.
Well, I think we'll leave it at that for now.
Okay.
The last question, and we always ask our guests, is I think yours might have quite a different answer to this.
Oh yeah, go on.
Considering your what's it called? Well, we'll leave that word somewhere blank. What are your hopes and dreams? Who you see yourself being now that you are, on the journey to become, let's say, highly advanced professional physicist. Do you see yourself working in dark matter? Do you see yourself working more on education? Who do you see yourself be? Like a research scientist, or do you want to be a professor one day? Who are you?
I like it. I'm really enjoying bathing in physics for 4 years, which is, what a PhD here means. So that's a luxury in itself, because I have been in the real world. I think my first preference would be to continue mostly in physics research. I don't think it necessarily has to be dark matter. I think because there's a possibility that dark matter simply won't ever be detected, or at least not in the next 20 years, in the kind of experiments we're running. And so, obviously it would be exciting if it is discovered, and I'm open to the idea. But maybe something like one of the more established things, like looking at neutrinos. There's a ton of stuff we don't understand about neutrinos, and there's some of the edge case stuff that's quite fun with neutrinos that is beyond standard model. So it might be more rewarding to focus on something where we know we're likely to push the frontier in a more interesting way than just saying dark matter doesn't have this particular mass. I would like to use my pedagogical skills and experience to push things along, but I think I want to mainly stay within the research and the physics rather than the pedagogy. So it might be that in the ways I've kind of making this sort of amateur effort here as a student, in a similar way, I'd probably like to be doing some sort of amateur effort as a postdoc and whatever after. I'd be open to being a prof. I happen to suffer from work-related stress. And so the idea of being told, here is 800 students, go teach. Something like that's intimidating. There's the managing of the overall workload, managing a team of students. There's all this stuff that being a professor means beyond just doing some physics. So some of that looks intimidating from the outside, but I don't know. I'm keeping an open mind. I did the PhD because it gives me two career options I wouldn't have had otherwise, one of which is this kind of route, the other being working in the private sector, doing anything where someone wants data analysis done. Right, probably some big pharmaceutical company playing with protein designs and folding, but so I'll see. I mean, I'll see what's available.
All right. Oh, that's great. Well, thank you, John, for coming. And I know you have a little cut off, so we're gonna cut it our episode here, and Patrick's gonna tell a story.
Today's story is related to all of our talk about dark matter and physics education. And with this, it's important to understand where a lot of these ideas relating to the existence of dark matter came from. We have mentioned both in this episode and through other episodes in our show, several historical figures in dark matter research that were very important to laying the foundation before the term dark matter was even a thing. This includes Lord, now Baron Kelvin in this episode, who we mentioned briefly about his observations about dark bodies in the heavens that were not visible by telescope, but the effects of their mass could still be observed. We wouldn't be focusing on Kelvin today, and you can actually go to our previous episode, which I will link down below for more information on him, but instead we will focus on someone more pivotal to dark matter research itself. And yet, though they are pivotal, they're often overlooked, or at least they were by contemporary colleagues. And this person is truly fundamental in determining that dark matter actually existed and building on theories that were developed in the 1930s. Today's story is about the person who confirmed the existence of dark matter, kickstarting this very fascinating field of study that is now intensely researched today. That person is Vera Florence Cooper Rubin. Vera Rubin was born on July 23, 1928, in the United States city of Philadelphia to Philip and Rose Cooper. Rubin's father was an electrical engineer at Bell Laboratories, and her mother also worked there until the two were married, but we won't get into that right now. At the age of 10, Rubin's family moved to Washington, D.C., where her interest in astronomy began from watching the stars out of her window. She was even able to build a telescope, albeit a bit crude, out of cardboard, and observed and tracked meteorites. During her time living in Washington, D.C., an area which she never truly left for the rest of her life, she attended high school at the Coolidge Senior High School, from which she graduated in 1944, not long before the end of the war. Inspired by the mid-19th century astronomer and naturalist Maria Mitchell, Rubin attended Vassar College, a then all-girls college in New York, to study astronomy. This was in spite of advice, including from her science teacher in high school, to study art instead of science. And this was a common belief at the time that science wasn't for women. Now, Rubin did study science, and for her undergraduate degree, she was the only astronomy graduate when she graduated in 1948. Having her sights set on a master's degree, she was denied from Princeton because of her gender. And it's actually also kind of funny because she had turned down an offer from Harvard as well. It was shortly after graduating from her undergrad that she married her husband, Robert Rubin, who would be her husband until his death in 2008, who was a mathematical graduate student at Cornell University. Rubin then enrolled in a master's degree at Cornell, where she completed her master's in 1951. The research conducted during her master's at this time focused on the motion of galaxies. She was able to work with Martha Carpenter, who was the first woman faculty member in the Cornell University College of Arts and Sciences, along with Philip Morrison, who was a key member of both the Manhattan Project and SETI, the Search for Extraterrestrial Intelligence. She also worked with Hans Bethe, who won the 1967 Nobel Prize for his theories on stellar nucleosynthesis, and Richard Feynman. Need I say more about him? While some of her research was later disproved, early evidence from Rubin's observations of astronomical objects like galaxies suggested a supergalactic plane, which was met with a lot of controversy and disagreement. The talk that she gave concerning these results of a supergalactic plane at the American Astronomical Society were controversial, not only because of the results and the fact that she wasn't a member, but also because she was visibly pregnant. While this research was not published because of the controversy and the overwhelming negative comments about it, Rubin went to Georgetown University after her master's to pursue a PhD in astronomy. At the time, she was 23, was pregnant too, so that's even more of a challenge to complete when you have kids. But she worked with Frances Hyden before being recommended to her future PhD advisor, George Gamow. Rubin completed her dissertation in 1954, which was concerned with how galaxies clump together instead of being evenly distributed. Again, this was controversial at the time because it was assumed that galaxies were just kind of spread evenly throughout the universe, but her findings showed that no, they do actually clump. After finishing her PhD, Rubin went on to be a mathematics and physics instructor at Montgomery College in Maryland for a year. Then for the next 10 years, Rubin worked at Georgetown University, first as a research associate astronomer, then a lecturer, before she finally became an assistant professor of astronomy in 1962. During her time at Georgetown, she collaborated with Margaret and Jeffrey Burbidge, sometimes called the power couple of astronomy at the time, where they focused on the rotation of galaxies. 3 years later, still keeping in mind that she was interested in the rotation of galaxies, she left Georgetown University to take a position at the Carnegie Institution of Washington as a staff member. It's there that she met Kent Ford, an instrument maker who would end up being a longtime collaborator. And I know even in personal writings of my thesis in my master's, her name and Ford's name were typically shown together because of their discoveries and some effects that are named after them. It's noted that a lot of her work was done from home at this time because she did have 4 young children, and I do just want to note that all 4 of her children went on to get PhDs in various sciences, with her daughter Judith Young becoming an astronomer in her own right as well. Now, Rubin's continued interest in the rotation of galaxies in her new position led her to apply for using the Palomar Observatory to make further observations of galaxies and their movements and their rotation. She became the first woman to legally use the observatory, but had to go so far as to build her own bathroom, since no facilities were available for women at the time, which, again, is just ridiculous. And it was here that she worked with Ford and his instruments, primarily a spectrograph, to make observations of the galactic clusters evidenced in her PhD work. From this, the Rubin-Ford effect was discovered through the observations of spiral galaxies. This effect shows an anisotropy, or essentially an inequality in the expansion of the universe at a scale of about 100 million light years, so it's not expanding evenly in all directions. Once again, this was controversial, but groundbreaking, or should I say space-breaking, and truly monumental work to show how the large-scale structures and patterns behave in the universe. And I mean, 100 million light years, that's very large scale. However, out of the interest of avoiding further controversial topics like quasars or other new but questionable astronomical phenomena, Rubin turned her attention back to the rotations of galaxies themselves instead of these larger scale movements. By examining spiral galaxies and observing their movement, especially using spectrographs and other types of observational equipment, she was able to show that the rotation curve of luminous, also known as light emitting matter, was flat for most of the radius of a galaxy. Now, this was contrary to the idea that objects further from the galactic core should orbit slower, and really didn't track with what was being observed, in which all the luminous matter did have a distribution that wouldn't be this kind of flat velocity no matter where you were along the radius, aside from very close to the center of the galaxy. As a quick visual for this, in our solar system, it takes Earth about exactly 1 year to orbit the sun. However, if you move to a planet that's closer to the sun, such as Mercury, it only takes 88 days, or about a quarter of a year, to orbit the sun. Meanwhile, Neptune takes about 165 years. So the further you go out, the longer it takes for you to orbit the center of mass, in this case, which is the sun. Now, if our solar system were matched to the dynamics of these observed spiral galaxies, all of the planets would take the same amount of time to orbit the sun, more like a solid disk rather than a Keplerian motion. These observations led to the conclusion that these galaxies must contain about 5 to 10 times the mass of what is actually visible through luminous matter. This gave credence to the idea that dark matter that was initially proposed, and that term was proposed by him, by Fritz Zwicky in the 1930s. This discovery of a dark matter halo that existed in galaxies that kind of evened out the mass distribution was confirmed and also supported the discovery of the cosmic microwave background and gravitational lensing. So a lot of these findings from Rubin went on to help answer questions that we had about other things, such as anisotropies within the cosmic microwave background, and why gravitational lensing was happening even though there wasn't any luminous mass present. Now, Rubin was also interested in the issue relating to the counter-rotation of galaxies. So this is where stars and gas in a galaxy move counter to the average rotation of the galaxy. So if everything's moving clockwise, some stars and gas might be moving counterclockwise. This was also an important question and important to understand why this was happening, and it was initial evidence for galactic mergers and also led to questions about how galaxies formed in the first place. Now, Rubin continued not only her research, but mentoring and science outreach, especially for women in science, to get women encouraged in science. There were a lot of cases where she would be the only woman present among a sea of men, and she really worked to try and improve that and have girls and women interested in physics and astronomy and researching in the sciences. She also received numerous recognitions and awards, such as the Gold Medal of the Royal Astronomical Society, and she was only the second woman to receive the prize at the time, the first being Carolyn Herschel, who won the medal in 1928, leaving a 168-year gap. She was also the author of several works that weren't research papers, and I would recommend reading her book, Bright Galaxies, Dark Matters, where she goes into her experience and her research as a woman in science. A quote from it is the following, quote, "I live and work with 3 basic assumptions. 1, there is no problem in science that can be solved by a man that cannot be solved by a woman. 2, worldwide, half of all the brains are in women. 3, we all need permission to do science, but for reasons that are deeply ingrained in history, this permission is more often given to men than to women." Unquote. I do hope that quote helps to illustrate her drive to create a more equal standing of women in science and better representation and inclusion within the sciences. And I think the fact that she faced so much adversity while still making these incredible discoveries, it speaks to the monumental effort that she underwent to ensure that she was still able to do science and something that she loved and appreciated while encouraging others to do so. Unfortunately, on December 25th, 2016, Rubin passed away in Princeton at the age of 88 and was still researching and mentoring up until her death. Her legacy certainly lives on, though, including with the completed, but still not quite ready to go. It's currently being tested. Vera Rubin Observatory, built in Chile, that will investigate dark matter and dark energy through astronomical observations. Many other instruments and awards have been named after her. A fun one is that there is a CPU named Vera and a GPU named Rubin from NVIDIA that are for data processing centers. And I really hope that's used for dark matter research and astronomy in some sort of computing cluster. She can also be found as a lasting legacy in most work relating to dark matter. Again, I've mentioned that I've talked about Rubin's work and her discoveries in my thesis, but it's very common for someone in dark matter research to know her name. Unfortunately, it's not as well known outside the field. But considering the uphill battle that she faced in a male-dominated space, her lasting impression, both in terms of science itself and inclusion in science, is really encouraging to see. So, the next time you're at, say, a trivia night where someone is asking a question about women in science and how it can be equal, don't fall back to the standard answer of Marie Curie. While also an incredibly notable woman in science, there are so many others like Vera Rubin or Rosalind Franklin, who was not attributed to helping with the discovery of DNA for the longest time and the double helix within it. But I encourage you to look into a field that you're interested in the sciences and just see the important women that are at its foundation.